Welcome back, everyone. This is Mr. Fawcett with another lesson in our AP Calc AB journey. Today we're going to talk about continuity over an interval. Now, the last couple of videos we talked about continuity at a specific point. We talked about a three-part definition that we need to use to justify whether a function is continuous at a certain point. So now we're just going to expand that and talk about whether a function is continuous over an interval. So this lesson is going to be two parts. The first part is not going to deal with a lot of calculus, but we're just going to talk about continuity in general and break down some different classes of functions and discuss when those functions are continuous, when those functions aren't continuous. And then in the second video, we'll talk about the definition of continuity over an interval. And look how to apply it. So let's start off here by looking at the graph of a function, and it gives us 4 intervals. And we need to discuss whether the function is continuous over each of those intervals, and if it's not continuous over that interval, we need to talk about where it's not continuous. So as always, I encourage you to pause the video, give each of these a shot, and we'll come back to discuss once you're done. Okay, so hopefully you've had a chance to work through all of these. Before we get going, let's first discuss what the idea of continuity is. And the very basic way that it's usually introduced, I think, is can you trace the function over the interval without picking up your pencil or your finger or your pen, whatever you're using, right? And that's a pretty good visual, right? But it's not a sound definition, but it is an easy way to introduce the idea of continuity. And even though we have more precise ways of describing continuity, it's something that's pretty useful when we're just looking at a graph, because it's a quick and easy way to know whether the function's continuous, and then we can worry about proving it later on. One other thing to note is that, right, we have brackets versus parentheses. So in purple, with the brackets, that means we're including that number. So the interval includes -4 and 2, and down with the parentheses, we are not including the ends of those intervals. We're not including the numbers -2 and 3. So hopefully we were aware of that. Okay, for the interval -4 to 2 inclusive, okay, with a quick look, we can see that the function has a discontinuity at x equals -2, right? We have this jump discontinuity here. Other than that, it would be continuous, but because we have the discontinuity, it is not continuous over the entire interval, and we just want to state where that discontinuity occurs. So at x equals -2. And again, if you're not familiar with jump discontinuities, a jump discontinuity is when the limit, as we approach the value from the left, so as we approach -2 from the left or the negative side, right, that limit is different than as we approach from the right. So that's what it means when we say, or that's what I mean when I say jump discontinuity. Okay, next interval, we have -2 to 1. So -2 to +1. Now we are including -2. So we would need to be able to, I'm actually going to start from 1 because the function is continuous at 1. And we would need to be able to trace all the way back to -2. Now we're okay right until we get to x equals -2, right? Because then we have this jump discontinuity that we talked about before, which means the function is not going to be continuous over this interval. Now, if we had the interval parentheses -2, comma 1 with a bracket, right? So where we're not including -2, then it would be continuous. But since we have to include 2, this function is not continuous over the interval for the same reason as number 1. So no I'll just write it out again. Jump discontinuity at x equals -2. All right, our third interval, we pick up some parentheses. So this time we're going from -2 to 3, but we are not including -2 or 3, right? And that's good because we have discontinuities at both -2 and 3. But as long as we don't have to include those, we are able to trace the function over that entire interval. So we're A-OK here. The fourth one, we are going from 0 to 3. But this time we have to include 3 in our interval. And we're okay at 0, but at 3 we have a discontinuity, namely a point discontinuity. So the difference between a jump discontinuity and a point discontinuity, for a point discontinuity, the limit exists at that point, right? So if I am looking at the limit as we approach 3, the limit certainly exists. That limit would be 0, even though the function is not defined there. So there's a point discontinuity. Remember, as I was explaining the jump discontinuity, the limit at that x value does not exist for a jump discontinuity because the limit's different for both the left and the right side. So down here, the answer is no, right? Point. And another name for these is a removable discontinuity, so either one works. So point or removable discontinuity at x equals 3. Okay, so let's erase this. And now we're kind of going to do the opposite. We're going to work backwards. They're going to tell us, they're going to give us a description of a function, and we have to now draw what that function looks like. And of course, you could have an infinite number of answers here, but take a second and try to sketch one out yourself. Look at the two constraints, A and B, and see if you can draw a function that matches those constraints. So real quick before you get going, I did have to make a quick change when I went back and edited this video. You are looking at a jump discontinuity rather than a point discontinuity. So if you just suddenly saw those words change just because I went back and edited it, just to make this question make more sense. All right, so attempt it on your own, and we'll try it in a few minutes. Okay, so first thing to look at is our 3 intervals. Actually, first thing to look at is this continuous strictly statement. So this function is continuous strictly over these 3 intervals, which means it's not going to be continuous anywhere else. So it does matter that we stick specifically just to drawing the function between those intervals and not putting arrows on the end and showing that it continues past -7 or past +7, because it doesn't say anything about that. So now our first interval, we have -7 to -4. We are including -7. We're not including -4. Before we just jump ahead and draw this interval, we kind of should come up with a plan regarding our vertical asymptote. That was a very poor star. Our vertical asymptote and our jump discontinuity. And do we want to put the vertical asymptote between the first two intervals, or do we want to put it between the second and the third interval? And if we have a vertical asymptote, the function is not going to be defined at that x value, right? Because if both one-sided limits are approaching either positive or negative infinity, the function is not going to be defined at whatever x value that vertical asymptote's at. So we need to look for intervals where the function's not defined at that x value, and that's where we're going to put our vertical asymptote. And that just happens to be at x equals -4. We cannot put it between the second two intervals because x has to be defined, or sorry, the function has to be defined at x equals 0. So we just can't have a vertical asymptote at x equals 0, right? Because the function can't touch or cross a vertical asymptote, so it can't be defined at that x value. Okay, so enough of that. I just wanted us to plan a bit ahead. Let's use green. And we'll use pink for our last interval. So if we look at our blue interval, we're going to pick a value for x equals -7. We'll pick that y value of -3, and I'm going to have it approach positive infinity. Okay, remember we have that vertical asymptote at x equals -4. And for our green interval from -4 to 0, let's have the function come up from -infinity, and we'll have it end right here at x equals 0, where it has a y value of 2. So again, your functions could be either approaching positive or negative infinity. It doesn't matter. It doesn't tell us which one they have to approach. They just have to be approaching one or the other because there is that vertical asymptote there. If we look at our last interval, the one in pink, the interval is 0 to 7, and it does not include 0, but it does include 7. So here we are going to have a jump discontinuity. We need to start the function at a y value other than 2, because then otherwise it would be continuous at 0. And we can have the function do whatever we want as long as it is defined at x equals 7. So I'm just going to have it be a linear function. Okay, couple things that you need to make sure you have. You need to make sure you have your vertical asymptote at x equals -4 and your jump discontinuity at x equals 0. And you also need to make sure, that these are closed points in blue, and you have that one open point in green. Okay? If you have those, it doesn't really matter what's going on with the rest of your function, as long as those are correct. Let's look at number 6 real quick, and then we're going to end part 1 of this video. I think it's going to actually be 3 parts. So it says, given your function, where does it have limits that where does it have a limit that does not exist, or limits that do not exist? So if we look at our graph, 2 spots should jump out at us. I'll give you 15 seconds to think about it, and then we'll discuss what those 2 spots are. Okay, so hopefully we notice that when we have a vertical asymptote, the limit does not exist. Right? We're not talking about infinite limits yet, so for now, whenever we see a vertical asymptote, we just say the limit does not exist, and that's going to be at x equals -4. And whenever we see a jump discontinuity, right, that also means the limit does not exist, because the limit from one side is approaching a different value than the limit from the other side, and this is at x equals 0. Okay, we are going to end it here for part 1. In part 2, we are going to be talking about, or exploring rather, the different classes of functions. So we're going to look at polynomials, we're going to look at rational functions, composite functions, exponential functions, and radical functions. And we're going to explore and discuss when those functions are continuous and when they're not continuous. And we're going to think in a general sense across the entire class of functions, rather than just coming up with, this specific polynomial is not continuous at this point. We're going to try to think a bit more generally. So hope to see you then. Until then, this is Mr. Fawcett. Enjoy the rest of your day.